Hello, and welcome to AP Physics with Brian Lee, Akash Venkat, Jeremy Long, and John Zhang. In this video, we'll be teaching you about AP Physics C mechanics. Now, in order to first understand mechanics, you will have to understand what a system is. A system is basically any object or group of objects that you are interested in. Suppose, let's say, this one ball, it might be in my system, or it could be multiple balls, like this cue ball, this 7 ball, and maybe that 8 ball. Whenever there are interactions between two systems, forces arise, and these forces are what eventually leads to changes in motion. There are 3 major changes in motion: rotation, translation, and oscillation. Now going back to the interactions, there are 4 major types of interaction. Contact interaction. The second would be elastic restoring interaction. Third, tension. And fourth, gravitational pull. All of these interactions lead to 6 different types of forces: friction, drag, normal, spring, tension, and gravitation.
Contact interactions create direct forces that arise when two systems come into contact with one another. Frictional, drag, and normal forces are all examples of contact forces and can be seen throughout our daily lives. The very first force that arises from a contact interaction is the normal force. The normal force is the support force exerted upon an object that is in contact with another stable object. The contact force arises because the surface holding the object resists compression and exerts a force that is always perpendicular to itself. As you can see, the normal force is always perpendicular to the surface, even on an incline. The second type of contact force is called the drag force. It's a resistive force that impedes the motion of objects when they travel through fluids, which are just liquids and gases. It always points in the opposite direction of the motion and is caused by the collision of the moving object with the particles of the fluid. In the equation above, the F, it stands for the drag force, the P stands for the fluid density, or sorry, I don't think it's called P, but it looks like P. A is area in front of the fluid's velocity, V is the fluid's velocity, and C is the drag coefficient. Now finally, the last force is friction. Friction is a force that resists the relative motion of 2 solid surfaces, fluid materials, or material types when they slide past each other. There are 2 types of friction: kinetic and static. Static friction will always be greater than kinetic friction for the exact same object simply because the coefficient of static friction is always greater than the coefficient of kinetic friction. Kinetic friction is always directed in the opposite direction of the motion of the object, while static friction is always directed in the opposite direction of motion that the object wants to move in. Lastly, frictional force is also directly proportional to the normal force of the object and does not depend on the surface area or relative speeds of the object.
The next class of interactions which are frequently encountered in introductory mechanics are spring forces. Spring force due to elastic deformation of a spring or other solid objects which would restore to an original configuration with no such interaction. In other words, elastic restoring interactions, they are a mathematical approximation to the restoring behavior of springs and other elastic solids under small deformation.
We know that elastic restoring forces are a direct application of Hooke's law, and from what we know so far, a spring has a restoring force of F equals negative K delta X. This means that if you choose the origin as being X equals 0, then compressing the spring would correspond to a negative X, which essentially means it's displacing the spring to the left, and stretching the string would correspond to a positive X, which is stretching the spring to the right. In that sense, by extending the spring, a positive delta X creates a negative force, which is negative 1 times delta X, and that acts to restore the spring to equilibrium. And that's basically saying pulling back on the spring extension. And by compressing the spring, you would have a negative delta X multiplied by negative 1 times delta X, which creates a positive force that effectively restores the spring equilibrium, proving F to be equal to negative K delta X.
Tension interaction is an interaction involving the force of tension, in which the force is transmitted through a string or wire when it is pulled tight by forces acting from opposing ends. The tension forces arises because the taut string resists extension. The tension force is directed along the length of a wire and pulls equally on the objects on the opposite ends of the wire. In the example above, 2 people are pulling on the rope in opposite directions from opposing ends. The tension force pulls equally on the opposite ends of the wire. Bridge designers also take into account of tension and compression forces when designing bridges. In the bridge above, the tension forces are shown in the red.
Gravitational interaction is an interaction involving the force of gravity, in which an attractive force is present between two objects, simply because they both have mass. Gravity is a force with no origin that is one of nature's fundamental forces. Examples of gravity include the falling of an apple from a tree and the attraction between the sun and the earth, as well as the attraction between the earth and the moon. Essentially, in the universe, every object is pulling on each other. Newton's law of universal gravitation states that any two bodies in the universe attract each other with a force that is directly proportional to the product of their masses, and inversely proportional to the square of the distance between them. This can be shown in this equation, where F of g is the force of gravity, g is the gravitational constant of 6.67 times 10 to the negative 11th, m1 is the mass of the first object, m2 is the mass of the second object, and r is the distance between the two objects. For a system to undergo rotation, the line of action of the net external forces acted on an object does not pass through the center of mass. The ability of a force to produce rotation is defined as torque. The equation of torque is torque equals force times distance times sine of theta, where theta is the difference between the direction of the force and the direction of the object that is moving. In a single body system for rotation, angular velocity is the state variable. The single body system for rotation is supported by the net torque model, which is supported by Newton's second law.
Rotations for multi-body systems are slightly different from rotations for single-body systems. For a multi-body system, the state variables are angular momentum and total mechanical energy. Rotations change the values of the state variables due to work being done on the system and the impulse created by the torque.
For a system to undergo translation, the net external force must be applied at the center of mass of the object. When translating a single-body system, velocity is the state variable that can be changed when a force is applied. Based off of Newton's second law, F equals ma, a force applied will cause some form of acceleration, which will in turn change the velocity of the system.
When describing the motion of objects in a multi-body system, momentum is essentially the same as using velocity if you were to be describing a single-body system. Translation still occurs when a net external force is applied at the center of the mass of the system. Momentum is a vector describing how difficult it is to stop a moving object. It's given to us by P equals mv. When using momentum to describe motion, the effect of interactions are manifested as impulse, which is the integration of Newton's second law, F equals ma, with respect to time. An interesting fact is that Newton's second law wasn't stated in terms of a force's effect on accelerating mass, but rather a force's effect on an object's momentum. The fundamental momentum model is therefore called momentum and external impulse. The model essentially states that the system's momentum can only be changed by external forces, since the internal effects are cancelled by Newton's third law. When momentum is transferred between objects in a system, energy is changed after the work is done on the system. However, this is just a fancy way to say that the translation has actually occurred.
The third and final type of motion that we're going to be talking about today is oscillation. A system that is undergoing oscillation is modeled by the restoring force model and is backed up by Hooke's law. In short, oscillation of a system is a system in which a particle or set of particles moves back and forth. Whether it be a pendulum swinging back and forth or a spring compressing and stretching, the basic principle of oscillation maintains that an oscillating particle returns to its initial state after a certain period of time. This kind of motion, characteristic of oscillations, is called periodic motion and is encountered in all areas of physics. In every oscillating system, there is an equilibrium point at which no net force acts on the particle. A pendulum, for example, has its equilibrium position when it is hanging vertical, and the gravitational force is counteracted by the tension. If displaced from this point, however, the pendulum will experience a gravitational force that causes it to return to the equilibrium position. Take another example, a bobblehead. According to Newton's law of inertia, an object which is moving will continue its motion if the forces are balanced. Put another way, forces when balanced do not stop moving objects. So every instant in time that the bobblehead is at the equilibrium position, the momentary balance of forces will not stop the motion. The bobblehead keeps moving. It moves past the equilibrium position towards the opposite side of swing. As the bobblehead is displaced past its equilibrium position, then a force capable of slowing it down and stopping it exists. This force that slows the bobblehead down as it moves away from its equilibrium position is known as a restoring force. The restoring force acts upon the vibrating object to move it back to its original equilibrium position.